Okay, I thought we would start with a little bit of a review of what you guys covered in the lab. So in the lab, you built two actual working motors, and I just want you to talk through some of the things that were going on in the motor that you hopefully wrote up in your in your lab manual that I haven't graded it yet. So I have this loop that represents the much more functional loop that you're building. So let's just talk through what was going on with that motor. So imagine that, so imagine that you have a model of a motor. So one of the important part was that there was a magnet at the bottom. So for the model of the motor that you are working with, the world's simplest motor, it's not that important that this magnetic field is, we can assume the magnetic field is uniform. That'll make our calculations easier. So we can say, all right, I have a permanent magnet here that's producing some kind of magnetic field that we can say is uniform. There are other situations where it is important for the working of the device or whatever that you are working with. It's actually important that magnetic field is not uniform. This is not one of those. But it's actually pretty common where it's important that magnetic field is not uniform. Even something as simple as a permanent magnet attracting another magnet. If you place a permanent magnet into a uniform magnetic field, this actually will not feel any net force. It'll feel a torque, it'll turn, but once it has turned, then the force on the north end, force on the south end is the same, so they balance out. So for a permanent magnet to attract another permanent magnet, it's important that the magnetic field decreases as you go farther away. So that the closer end feels greater force, gets attracted more, than the farther end gets repelled. So, but in this simple example, you don't have to worry about the complication. You just have some magnetic field. And what you now have is a loop of wire through which a current flows. So there are 4 positions that we can think about. Position 1, position 2, position 3, position 4. The 1 and 2 and 3 and, 1 and 3 and 2 and 4 are different. So let me illustrate them. So position 1 would look like, so let me make red color 1. 1 looks like the current, let's say, comes into the board and then goes out this way, around, and then current comes out of the board. This is 1. Good? Position 2 will look like, let me do that in purple. So position 2 will, let's see, which way do I want this to turn? Sorry, I'm trying to figure something out. So let's say position 2 has a wire so that wire first goes into or out of the board, and then goes down this way, and then loops around, and then comes back, and either goes in or out, and I need to figure out, I want it to turn in the natural direction. So let's say I want it to turn in clockwise direction, then if, that's why I have this. If a current is going into the board at the top, then current will be going into the board here. L cross B. Okay, yeah, I think that's the direction I want. So, so on the top, the current goes into the board. On the bottom, current is coming out of the board. So this is position 2. Position 3 would be where this has turned another quarter turn. So position 3 looks kind of like position 1 with a slight difference. So let me kind of superpose it. So position 2 will look like so that current actually comes out of the board here. Current comes out of the board here, and current goes into the board here. So you can track this point, for example. So it has turned a quarter turn, another quarter turn. And so this is position 3. And when it turns another quarter turn, then it's not exactly like 2. It's once these two flipped around. So position 4 in green would look like this. So current, I guess here, current went into the board, and then, so imagine this loop. Current goes into the board, down, and then still in, and then up, and then completes the loop here by coming out of the board. Good. So that's the position 4. And what you saw in the lab is that this loop, it somehow, when you have a current flowing through it, somehow it feels a force. So it feels something that makes it rotate. So not a force, but torque. It feels a torque. And I want to make sure that everyone understood what was going on in the lab. So in positions 1 or 3, does this feel any torque? So that's where the loop of wire was lying flat against the magnet. Did you in the lab, you didn't observe it turning from the position, right? In fact, you have to make sure that you strip the wire in such a way that the current flows in this position. So that's because, okay, in this position, let's say there's a current flowing. Then position 1, current goes in here. So in this segment, current goes this way. So I cross B, force points in. All right, that's not going to turn anything. So on this segment here, I cross B, current points to the right. But, well, this is my center of rotation, so the lever arm for this force is 0. So no force. And I cross B, well, this still also points in, nothing generates no torque. And finally out here, I cross B, it also points in. So for position 1, all the forces, none of the forces on any of the segments generate torque, so it doesn't turn. Position 2 changes things. So current is going into the board here. So in the top, so this segment, there's no force at all because I can't cross anything. Its angle is 0 degrees. So no force along this segment. But there is a force along the top segment. I cross B. There's a force that's pointing to the right. There's a force that's pointing to the right on the top segment where the current is going into the board. Where current is going down, once again, 0 force. When the current is coming out of the board on the bottom part, there's a force pointing to left. Yeah. So if you place this loop in this position and let current flow, then this will rotate. It'll start to angularly accelerate because of the torque due to these two forces. Right? So have it keep going. And in position 3, it'll be the same thing as 1, except the other way around. But either way, in positions 1 and 3, there's no torque being generated. In the in-between positions, there will be some amount of torque. This is the position of the maximum torque. There will be some intermediate amount of torque here. You can calculate it if you want. So now at position 4, what happens? So the current is going into the board on the bottom portion. What's the direction of the force on this segment of the wire? To the right still, right? So any current that's going in, IL cross B, the force will be to the right. So there's a force to the right, and the top segment there should be force to the left. Yeah. So you see that in position 2 there was clockwise torque, but in position 4 there's going to be counterclockwise torque. So this is why in the lab you are supposed to peel off only half of the wire, so that essentially you have current flowing in one of these two positions, but when it goes to the other position, it doesn't make any electrical contact anymore, no current, no force, so it just keeps rotating from the angular momentum of the previous rotation. So it just rotates through the position. When it comes back to 2, that's when it gets another push, and then when it comes back to 2, another push, comes back to 2, another push, and so on. Yeah, and in the lab, you should have seen that if you strip it both, sometimes it still works. It doesn't necessarily always not work. It's a question of, is this amount of force the same? So if somehow the amount of force is slightly different for positions 4 and 2, then it won't completely cancel each other out over one full turn. So, all right, so everyone got this during the lab, right? This is not all that new. Okay, so the part that I wanted to go over was the part that took longer for people to get. Is so if you're thinking of something that's rotating and there's so let's say get rid of position 4. Let's say we oriented our loop or we stripped it off in such a way that the loop doesn't make any electrical contact when it's in position 4. So we got rid of this, and the only position that's generating any torque is position 2. So looking at it over one cycle, there should be a same average torque over one cycle, right? So this is motion with something like a constant torque. So that means it should be angularly accelerating, at the same average rate per cycle over time. And if you just approach it naively and somebody asks you, what is the maximum speed this can rotate in? Your answer would be, well, there is no maximum speed. As you keep applying torque, it'll move faster and faster and faster. And in theory, there's nothing that slow it down, right? But that's not what you saw in the lab, right? You actually measure the rotation frequency of the motor, and it seems to be pretty constant. So the question that was asked was, all right, so what determines what the maximum speed of this is? Like, why doesn't it keep rotating faster and faster if the torque due to magnetic field always goes in the same direction? In other words, when you have a motor, I don't have any actual motors. Well, when you have a motor, what limits how fast a motor can spin? Yeah, so voltage is the intuitive guess that a lot of people come up with. As in, so you are looking at this position 2. So to these 2 wires, you are applying some amount of voltage through the battery, right? And you have some intuition that if you increase the voltage of the battery, that instead of one battery, if you had 2 batteries, then it would spin faster. Right? Just like, if you have 2 batteries in series instead of 1, and you hook them up to a light bulb, then the light bulb shines brighter, at least until it burns out. So that's a good intuition to have. The question we want to address is why? Because if it's a matter of, so when you are looking at, question is why? Why does the voltage being applied have any relationship with how fast it's spinning? Because, voltage that's being applied, naively you'd think, okay, that there's some relationship with how much current is flowing. And you'd think, all right, so there's something to do with the amount of force. So there's something to do with the amount of torque. But at that point, there's nothing that relates it to the maximum rotational speed. Right? There's nothing that you see here that says when it's spinning this fast, there's some torque that's going the other way. Yeah. So another guess would have been that, well, maybe it's maybe it's a friction that, so as this keeps rotating faster and faster, the retarding force due to friction, at some point it gets bigger and bigger. So easy guess to make as well. The maximum speed is such a speed so that the torque due to magnetic field is equal to the torque due to friction. And so here the answer is a little more complicated than that, although it's a little bit related. So you have seen something that kind of acts like a friction, but it's not really friction. That's this demo that everyone got to play with a little bit, right? So this is, it's just copper tube. It's not magnetic in any sense of the word. I have not two magnets. One of them is a piece of iron. The other one is an actual magnet. So let's see. Neither of them attract copper. But I mean, that's expected because this is not magnetic. It's not ferromagnetic. So you see the difference when you put this through the tube and let it drop. I actually don't know which is which. This could be iron or the magnet. Okay, it's the iron. So this is iron. It simply drops, and nothing funny happens. When you drop the magnet, though, it doesn't drop as fast as the piece of iron does. It drops much slower. How did we explain this last time? Yeah, eddy current. That you have a moving magnet, and we introduced the Faraday's law last time. Faraday's law says that the line integral of E dot dl is equal to minus the rate of change of magnetic flux. And actually, Faraday's law is the one law where I'm not really going to expand on this portion too much. So far with the Gauss's law and Ampere's law, we didn't care about the integral. We cared about the actual the field, right? With the Faraday's law, voltage sounds like a quantity that I actually care about, right? So I'm going to choose to express this as the induced voltage. So induced voltage, as you go around the closed path, is equal to this, minus the rate of change of magnetic flux. So when you allow this magnet to move through the copper, it's causing the magnetic flux, for example, magnetic flux through the surface that's enclosed by this loop change. So as the magnet initially approaches, let's see. You know what? I don't know which end is north and south. Let's pretend that the top is north and the bottom is south. So magnetic field points up mostly, and it gets weaker as you go farther away from the magnet. As the magnet approaches this top portion, what's the direction of change of magnetic flux? Is it changing more downward or more upward? Think carefully. So, wait, you're right. Yeah, changing upward. Well, okay, south end. So magnetic field is pointing into the south end. It's going from weaker to stronger. Yes, upward. Yeah. So as it approaches, magnetic flux is changing in the upward direction. What about after it's passed through? As it drops past that point, is the magnetic flux? Think about it carefully. So magnetic field, so this is now below. Magnetic field still points up. As it continues to move down, it's still pointing up, but gets weaker. Wait, does it change direction? You're right. It actually changes direction. Yeah, you're right. Yeah. Okay, so I was mistaken. Yeah. Thank you. So okay, as it approaches, the magnetic flux is changing in the upward direction, and then once it passes through, then the magnetic flux is changing in the downward direction. Yeah. So in both of those cases, change of magnetic flux induces a voltage. That voltage generates current around it. And that current now generates magnetic field. That's Ampere's law again. And the magnetic field that's produced by the current is oriented in a direction that opposes the movement of the magnet. So this is, I guess, the most demo I have. But I have a video that's maybe a slightly more impressive because the guy has a more impressive magnet than I do. It's a video I use for my other class, but I think it's a useful demo as something that's more interesting than a magnet moving through a pipe. Let's see. It's this one.
This is a very large industrial strength magnet. It's made of rare earth metal, neodymium magnet it's called. It's made of iron, boron, and nickel. And it has two sides, the north side and its south side. And this is a piece of pure copper. And what the magnet induces in the copper is called an eddy current. It basically generates small pools of swirling electrons to resist the movement of the magnetic field that this induces on this. So what that does basically is resist that magnet from falling like a normal object on like a piece of wood. So it kind of cushions itself, as you can see.
Yeah, and you can see it when he pulls it. It has to exert greater force than the weight.
Onto the copper from the magnet itself. So without touching, I can move a piece of copper. And that's basically what I do here at Magnet Drive is I use a bunch of these to spin a very large disc.
All right,
and that
10
disc
seconds.
induces torque, and that creates a coupling without actually touching one shaft to another. So that's my job.
All right. So, that's something that happens with the magnet and around the conductors. And I guess the intuition I want you to have is that this almost acts like a friction. It's a frictional force that's dependent on the velocity. The faster the magnet is moving, the stronger the force is. In fact, I haven't tried this. Let's see. Do you see if I move this up as it's falling, do you see the magnet getting dragged along with the copper tube? Right? Yeah. So this is the kind of frictional force that I want you to think about. That the effect of this Faraday's law is that it creates something that looks like a friction force. So that's what I want you to think about here, that as this loop rotates through, it's a conductor moving in a magnetic field. So there's going to be something that kind of acts like a friction. So where you get the maximum speed, where you get, I guess I should really call it, where you get the maximum angular speed, it's determined by the retarding or slowing down effect from determined by, I guess, let me call it reaction. Reaction voltage from Faraday's law. And I actually have to explain myself a little bit. I swore on an oath to excise all the references to the word EMF out of my course. That's why I'm trying to come up with these non-standard terms. The phrase you will see in your textbook is back EMF. What I'm trying to call reaction voltage is back EMF in your textbook. I have to come up with a correct. When I called it back voltage, it didn't sound right. So what it means is that, so far, the working of motor that we are describing, it was just from Lorentz force, right? How much force is on the wire. Now, what we are going to look at is, as this rotates, there's going to be a voltage generated around the loop that's going through. And at the maximum speed that it's moving at, the voltage that's generated through Faraday's law, it's going to be exactly equal in magnitude to the voltage that you are applying. So when those two are equal, then essentially the batteries cannot push any more charges in any more than they were already going. So charges, there's still current going through it, but you kind of imagine them going through on their inertia. Like if you simply imagine this as a superconductor, you cause a current to flow, and you just remove the battery and let there be a current conducting path, then the current will just keep going based on its own inertia that was going before. And the maximum angular speed is determined by, well, how fast it is, how fast should it be rotating, so that the effect from Faraday's law, which tries to push the current back and slow it down, and the effect from that and the effect from the applied voltage balance each other out. Okay? And this is a simple calculation we can do actually. I think some of you are doing that during the lab. You're not required to do it in case you didn't do it. But since it's a relatively simple calculation, let me just go through it. So let me specify some parameters so that I can actually do the calculation. Let's say that I have to specify some parameters here. I have to know the area of the loop. And for the simplicity's sake, I'll say it's a single loop. I have to know the strength of the magnetic field. So let's say that the strength of the magnetic field is some strength B naught. And I have to know the applied voltage, which I already wrote down. I think that might be it. Do I need to know the resistance of the loop? I don't. In fact, I'm going to model this loop as having zero resistance. So if this wasn't working as a motor, it would actually allow infinite current to flow. Or it'll actually be shorting the battery. But what we can show here is that, well, it won't actually short the battery. So, so this is the statement that I would start out with. So maximum angular velocity is determined by the reaction voltage. More specifically, what we are looking for is that it's determined by when this reaction voltage is equal to the applied voltage of V naught. That's the condition that I'm looking for. So let me say that we are looking for the induced voltage to be equal to V naught. Yeah? To calculate the induced voltage, I need to use Faraday's law, which means I need to know this pesky magnetic flux. So that's where you have to go back and remember that, go back and remember all of this, that magnetic flux is given by magnetic field times the area. Or to be more careful, it's the dot product between magnetic field and the area vector. Good? Sometimes you have to do an integral, but here, because this is uniform magnetic field, I don't have to worry about an integral. So, so here it will be the strength of the magnetic field, B naught, times the area, A, times cosine theta, where angle theta would be defined in this way. So if I have this area, then this is the direction of the area vector, the normal vector, right? Did I do this? Oh, I did it. Sorry. We have a convention for assigning the direction of area vector, by the way. You use the right-hand rule. So when you have a closed surface that's enclosing an area, then you imagine going through the direction of the lateral right hand, 4 fingers, go in the direction of the current, or direction of the path that you're picking in the same direction as current. Then the direction of the thumb is the direction of the normal vector that has the same sign as the what you're picking. So here, the area vector actually points in this direction because current is going into the board and then out here. Okay? So the angle theta would be this angle here. This is the angle theta. Okay? All right, so that's the magnetic flux. So what we are going to do is using this expression here, write this as, well, V induced. Look at the Faraday's law. I'm just going to take the absolute value because I don't want to deal with the signs. So the absolute value would be the absolute value of the rate of change of magnetic flux. That should be equal to V naught. And peaking at this here, it would be where, so it's the absolute value of the rate of change of B naught A cosine theta. Which of these depend on time, so that when you take the derivative, it doesn't go to 0? Yeah, only theta depends on time. B naught, A don't. And the flux is changing over time because this angle is changing. Maximum flux to the 0 flux to the, so position 1, position 3 is actually the one with the maximum flux. Because your A vector goes up, so B dot cross A is the most positive, maximum flux, 0 flux, and then at position 1, you have the maximum negative flux. Right? So, yeah, writing all of that out, this derivative looks like this. It's the derivative goes through B naught at A, so B naught A, derivative of cosine theta with respect to time t, you have to apply chain rule. So derivative of the outside minus sine theta, and derivative of the inside, and d theta dt, that's my angular velocity. So that's my angular velocity. So at maximum angular velocity, this absolute value of this is equal to V naught. Yeah. You will see that, so this induced voltage is going to be a function of the angle theta, right? So to get the actual value, especially when you apply the voltage is kind of a square voltage, the way you built your motor, it looked something like this, right? With only half of it stripped off, voltage was at 0 half the time, and this maximum value at another half the time. So what you have to do is you have to imagine taking the average of the left-hand side and let that equal the average of the right-hand side. And, but this is the relationship that would give you the maximum angular velocity, and that's why the maximum angular velocity depends on how much voltage you're applying. It would also depend on how much magnetic field you're applying. And how much area the thing has, and all the other stuff. Okay. All right, so that's the review of the motor and sort of one application of Faraday's law.